Hello everybody, welcome to today's keynote. I'm pleased to be able to present virtually this talk on future challenges facing tumbling mills. Unfortunately, I'm not able to come to Lima due to some immigration issues in Uruguay, but I want to thank InterMet for the opportunity to present this paper remotely. So tumbling mill technology is over 100 years old, but it still remains a key part of most mineral processing plants that exist today. There are some new technologies that are starting to compete with tumbling mills in certain parts of the mineral processing flow sheets. So I want to take this opportunity to talk today about my opinions about what some of those computing technologies might do in the future and how they may substitute or may augment sag mills, ball mills, and other tumbling mills that we're familiar with. So for those who aren't familiar with tumbling mills, a tumbling mill is a horizontal hollow cylinder that's normally sitting on trunnion bearings at the two ends of the mill. The mill shell, the body of the mill, it rotates around a horizontal axis. Inside of the mill, there is a charge. So it's going to be partially filled, about a third to a quarter full by volume, with the material that you want to grind, which would be your ore particles. And more often than not, it includes some grinding media as well. So there is a variety of media that can be used in grinding mills. Autogenous media is literally you just take big rocks and you use those big rocks to grind the smaller rocks. And in the process of grinding, the big rocks will themselves become small and then will be ground by other big rocks that are entering the mill. More commonly in the sag mills and the ball mills, you're going to have steel media that's added to the mill. And the steel media, the steel balls, are going to be what does a large fraction of the grinding. There are some other grinding media available for certain applications. There's ceramic media that's often used in fine grinding. The key thing though for tumbling mills, we generally use two classes of them. We use a sag or an autogenous mill, an ag mill, when you're dealing with a very coarse feed. So you can come directly from a primary crusher into an ag or a sag mill. And then we use a ball mill to achieve the fine grinding sizes that we want for flotation feed or for gold leaching feeds and so on. So you'll normally see a circuit where out of a primary crusher, you feed directly into a sag mill. The sag mill processes that coarse material, 150, 100 millimeter size class, down to something on the order of 1 to 2 millimeters, which then gets passed to the ball mill. The ball mill will take that 1 to 2 millimeter feed down to a product size of something on the order of 100 to 200 micrometers. Tumbling mills can operate both wet and dry. Dry grinding requires something to push material through the mill. In wet grinding, obviously the water flows down the mill by gravity, and that helps to drag particles along with the water. In dry grinding, you generally use air for this. So you're blowing air into the feed end of the mill, and it's trying to push particles out the back end of the mill. And you normally would have a big grate at the back end that will hold coarse particles in, but allow the air and the fine particles out. Wet grinding is much more common than dry grinding in the mining industry because water is a much better transport fluid for moving particles in and out of mills. Also, the grinding mills don't operate alone. You normally would have them in closed circuit with a classifier of some sort. So we need to talk about the classifier as part of the overall grinding system, both with tumbling mills and with some of the alternatives that we'll talk to. For example, in a sag mill, you're normally in closed circuit with a pebble screen, and then the coarse pebbles that come off the top of the screen get recycled back into the sag mill, and those may or may not go through a pebble crushing stage on their way back to the sag mill. In a wet ball mill, you will take the product of the ball mill and pass it up through usually hydrocyclones, or you could use high frequency screens, with the undersize, the product, passing on to the next stage of the process and the oversize returning to the mill for more grinding. In dry ball mills generally use some combination of air classifiers, air cyclones, and possibly bag houses. You generally require much bigger equipment when you're dealing with air transport and air classification versus moving in slurries in water-based fluids. So dry ball mills, you'll typically have air being blown into the mill. You'll have dust particles coming out the backside of the mill, and then they'll go into probably 2 stages of classification, usually ending in a bag house, which is used to pull the finest material out so that you have a waste airstream that's not full of fine dust. So the competition that we're going to talk about to grinding mills, I'm going to put them into basically 3 categories here. So we're going to look at some of the dry technologies. We'll then look at a wet technology, which basically operates in the same environment as the current tumbling mills do. And then I'll look at a hybrid technology that is partially wet and partially dry. So the first dry technology we'll look at is vertical roller mills. These are widely used in the cement industry, and they can generally do the same duty as a ball mill does in a mineral processing plant. And you can get quite fine particles out of this. You can get down to 50 microns. The technology is a modern version of a trapiche or an edge mill that would have been used in colonial Peru and Chile. So you've basically got a big wheel that is moving around in a circle, and you place particles to be ground in front of the wheel, and then the wheel rotates on top of the particles, crushing them as it moves over. In the old systems, the wheel was what moved around the tabletop where the particles are to be ground. In the modern vertical roller mills, the mills are stationary, although they are on an axle so that they will rotate, and it's actually the table that rotates in the vertical roller mills. These are very energy efficient at grinding, but we'll talk in a moment, they're actually very energy inefficient in classification. So that's the first dry technology, is a vertical roller mill. The second technology is one probably everybody here is familiar with. It's the high pressure grinding rolls. These are widely used in the mining industry, and one of the largest installations is the Cerro Verde mine in Peru. These are very energy efficient in grinding, but in the size range where they work. The issue with them is that they require secondary crushing and they require dry screening, and they require a lot of ancillary equipment. There's a lot of conveyors. There will be some dust handling around transfer points. They're also particularly suitable to certain ore types and certain project types. So I think that in the future, there's probably 50% of the SAG mill market that could ultimately be taken over by HPGRs, but it's certainly not going to be 100% because there are some issues I've described in my YouTube videos where HPGRs are suitable for certain rock types but not for others. They're suitable for certain project types but not for others. A wet technology we're going to describe is stirred milling, and stirred milling is already widely used in the mining industry as well. It's generally used for fine grinding and for regrinding. So the stirred mill, rather than the shell of the mill rotating, the shell of the mill is stationary, and there'll be some sort of a stirring mechanism, and it could be an auger or it could be discs. There's a variety of different technologies. But the key thing is that this central rotating stirrer is what's moving, and it causes the charge to move. Now, these stirred mills, they can operate with a horizontal shell with a horizontal shaft, or they can be vertical. You can have a vertical shell with a vertical shaft. For this application, what we're probably going to be looking at is replacing ball mills with stirred mills, which generally means you're looking at these vertical type, the tower mill types. And these generally work at the coarser particle sizes in the fine grinding regimes. One issue with these mills is that they are power limited. There's only so much torque that you can put down these shafts before you run into problems with the materials of construction just twisting. So the largest of the tower type mills that are out there, you're looking at about 5 megawatts. In the future, they'll probably go up to 10 megawatts, but there is going to be a limit to just how much power you can transmit down those central shafts before you start running into issues with the shafts becoming too big or the materials of construction becoming too exotic. And the final competitive technology we'll talk about it's an experimental one, but it involves using high pressure grinding rolls in a finer grinding application. And in this situation, you're looking to replace the ball mill with HPGR. Now, one issue with this is that the HPGR dislikes wet feed. It wants a dry feed, but because of the particle size regime that we're in, you're going to require some wet screening here. So we'll talk a bit more about that in a moment. The HPGR itself is very energy efficient, and you see some very significant drops in the grinding energy required if you use an HPGR in a ball milling regime. But as we'll see, it's actually limited by the classification and the dewatering steps. So let's talk about classification circuits, because these are really important to the grinding world. So in the dry grinding world, you're generally looking at dry screening or you're looking at air classifiers. And the dry screening works in what we'll call the crushing regime. So you've got relatively coarse particles that are going to settle, and if you shake the screen deck, you can generally get those particles that are undersized to pass through the weave of the screen deck. The air classifiers are generally used in a grinding context where air at high speed can pick up particles and move them around. Materials handling by air classification is very energy intensive. It's a very inefficient fluid for moving particles around. And when you do the classification in air, you generally need some very exotic equipment like electrostatic precipitators or bag houses to get all of those fine particles out of the airstream. So air classification, it's expensive, and you generally will only use air classification when the ore must stay dry. Now, dry screening is not as big a deal. You are requiring things like conveyors to move this coarser material around. And in some of the HPGR circuits, you might cause a ton of material to be lifted up and dropped and lifted up and dropped 3 times in the process of going through secondary crushing, screening, and HPGR circuits. So materials handling, it can be as energy intensive or can even be more energy intensive than the milling circuits. Wet technology, this is generally much easier to design. You're dealing with pumps, you're dealing with pump boxes. The hydrocyclones are a very cheap piece of equipment you can use that will achieve an inefficient classification, but it's usually good enough. Wet screens can be much more efficient, but they're also much more expensive to use, they're more complicated to use, and they kind of limit the throughput that you can put through the circuit. The materials handling here is easy. You just run pipes. You use pumps. And it's much less expensive to pump material around in a water-based fluid than in an air-based fluid. Now, the damp technology that I described, it involves an HPGR, which you want to use dry, but then the particles that come out are going to be too fine to effectively dry screen. So you need to wet screen these. And one of the issues that we have with this technology right now is that the wet screening doesn't make an oversize that is dry enough for the HPGR to be very efficient, right? There's an issue here where we need to find a better way to keep dry material in the HPGR after we've wet screened it. So that's a bit of a question mark right now. And I'll talk through a possible circuit where we can avoid this situation of recycling wet material into a fine grinding HPGR. So the competition, vertical roller mills. In my opinion, these are generally not going to be competitive with tumbling mills. And it's the air classification that kills this option. Wet classification is just too efficient, and systems that rely on air classification are going to be limited to applications where you cannot use wet classification. High pressure grinding rolls. These are highly viable. These are an alternative to tumbling mills. They're already in use in a bunch of plants going around the world, and they do a similar duty to SAG mill. They are particularly well suited to competent ores. I make the argument in my YouTube video that SAG mills are better for low competency ore, and high pressure grinding rolls are better suited to high competency ore. And from a financial standpoint, you generally have a higher capital cost on an HPGR plant than you would have with an equivalent SAG plant, but you get the benefit of lower operating cost when you're running an HPGR plant than what you would see with a SAG mill plant. So the energy efficiency and so on, that can favor the high pressure grinding roll, where the capital cost favors the SAG mill. In the wet technology, stirred mills are a somewhat viable ball mill replacement, but the stirred mills do not scale up very well, and the maximum amount of size, the maximum amount of power you can put on a mill, when you get into these really large open pit mines, means you're going to need multiple units of stirred mills. So I think this option is going to basically limit it to lower tonnage plants. It just doesn't scale up very well. The other thing is that the stirred mills require fine transfer sizes, so they are suitable for being fed from a SAG mill, but in my opinion, they are not suitable for being fed from an HPGR in the form that we currently use the HPGRs. The high pressure grinding roll is going to have a transfer size that's roughly twice the dimension. It's twice as coarse as what you get out of a SAG mill. And that's probably pushes the product of an HPGR outside of the size envelope that a stirred mill can operate with. Another issue with the stirred mills is that we need media sizes that are suited to feed particle size. So when the feed particle size is coarse, a millimeter to 2 millimeters, you can't use some of the fine ceramic media that would currently be required in some types of stirred mills. So this requirement for steel media is going to limit us to these tower mill types. So this is to be like the Mezzo Verde mill, for example, the tower mill by Irish. FLS has its version. The higher speed mills that require ceramic media, so these would be your ISA mills and your HIG mills, they might have issues here because the media sizes are going to be too fine for the current generation of where we would want to use these stirred mills. This may change in the future, but at the moment, the media sizes in grinding balls, in steel balls, are going to be preferable to some of the ceramic media. So the use of high pressure grinding rolls in a ball milling regime, in my opinion, this is a very interesting technology. It's got some clear energy efficiency benefits, but it's not a full replacement for a ball mill right now. I think we could use high pressure grinding rolls in a secondary HPGR version that would replace some duty of a ball mill, but not all of the duty in the ball mill. The way to make this work, in my opinion, is you have to open circuit the HPGR. You're going to take down the product from your HPGR. You might have like a 5 millimeter transfer size, 4 millimeter transfer size coming out of a tertiary HPGR setup. In a quaternary setup, you might be able to make use of this. But you're still going to need a wet grinding stage after the HPGR to take advantage of the wet classification that you need to achieve classification of the fine particles. So in summary, vertical roller mills, I don't see these being a big part of the future for the minerals industry unless you have to operate dry. High pressure grinding rolls as a substitute for SAG mills, highly viable, they're already in use. The use of stirred mills as a replacement for tumbling ball mills, it's somewhat viable. It's probably going to get limited to the lower tonnages and to the applications with finer transfer sizes. So again, this would be SAG mills feeding ball mills. You could substitute a stirred mill into that ball mill stage. And the fine HPGR grinding, replacing some of the ball mill duty with an HPGR, it's not ready yet. I think it's an interesting technology, and I think that one's worth spending a little bit of effort thinking about and perhaps piloting for some future technologies. So what would one of these future circuits look like? I can see a situation where you've got a gyratory crusher as your primary crusher, feeding secondary cone crushers just as we do now, feeding a tertiary HPGR just as we do now. Tertiary HPGR is in closed circuit with screens just like we do now. And then the screen undersize goes to a quaternary crushing HPGR, which is still going to be dry, but it's going to be open circuit. So we'll probably take this from, let's say, the 5 millimeter feed down to something perhaps 700 micron. I don't really know what we'll end up with. But you'll end up with something that's done quite a bit of the ball mill duty in an open circuit HPGR. You'll then pass that product into a wet ball milling circuit, which can now be a lot smaller because the ball mill duty, some portion of it has been done in the HPGR. So you take advantage of the wet ball milling and the wet classification after you've taken advantage of the HPGR and its better grinding efficiency than a tumbling mill. So the ball mill is a finishing stage treating the fourth stage crusher oversized material. And you should be able to end up with a much smaller ball mill and a much lower circulating load. Here's a second potential circuit. This one we're going to look at it from the other way, though. We're going to go from primary crushing into a wet SAG mill, just like the SAG mills we have now. But the SAG mill screen undersize is going to get passed to stirred milling. And the stirred milling is going to be done in closed circuit. And you're probably going to have multiple units in parallel of these stirred mills, replacing what would have otherwise been ball mills. You can do a little bit more intense screening on the SAG mill to try and keep a tighter control on the oversize coming out of the SAG mill. Make sure that that's not passed into the stirred mill circuit. And it would look like this in terms of a flow sheet. So you're going to have the SAG mill screen undersize goes to a pump box, which then feeds the hydrocyclones. The hydrocyclones are probably not going to have enough head in their underflow to feed directly into the tower mills. So we may need an intermediate pump box here in order to feed the tower mills. But at least you're going to have the benefit of a closed circuit grinding circuit because you're feeding the sag mill product into the cyclone before it ends up in the tower mills, you're still taking advantage of the phantom cyclone effect and all the other benefits that come from sag mills treating a ball mill feed. This circuit is probably going to be a higher capital cost than a circuit involving ball mills, but it will probably also have much lower operating cost. You should consume much less power in these tower mills. Your media consumption is probably going to be lower. So you're going to have to trade off the higher capital cost versus the lower operating cost. But I think this is a viable circuit that some operators will choose to go with. How about hybrid circuits, going from a sag mill into an HPGR and then into the ball milling circuit or something like that? I don't see this being an option for the initial design, but I think you could put an HPGR on a pebble stream as a debottlenecking exercise. And what that involves is taking an SABC-A circuit where you're circulating pebbles around the sag mill, and then open circuiting the sag mill, putting extra crushing, and then passing that to the ball mills. Now, where this would typically happen is later in the mine life, where as your flotation circuit control improves and you learn how to do more with less in the float circuit, you can coarsen your product size coming out of the hydrocyclones. Coarsening the product coming out of the hydrocyclones takes load off the ball mills, which means that there's now unused power sitting in your ball mill circuit. And passing this material, these crushed pebbles, into the ball mills is a way to draw that extra load and make some use of it. So again, I think this is more likely to be used as a brownfield expansion. I wouldn't probably expect to see this as in a lot of initial designs for a bunch of reasons. How about HPGRs feeding stirred mills? I don't think that this is too realistic because the HPGR product out of a tertiary HPGR is too coarse to feed into the stirred mills as the technology currently sits. Now, perhaps what we could do is go take advantage of that fine crushing capability that we saw on the replacement of ball mills, some ball mill duty with an HPGR. You could do that here, where you go into a quaternary HPGR that is in open circuit, so you're doing fine crushing now, fine grinding in the HPGR, and then you're passing that into the wet classification circuit that goes around a tower mill. I think this could work. There is going to be an issue around the quaternary HPGR where you might get some coarse grit that you need to screen out before you pass that HPGR product into the tower mill loop. It's probably going to be a very high capital cost to build a circuit like this, but it's probably going to have a very low energy consumption compared to tumbling mills. So there might be applications where electricity is particularly expensive, where something like this could be attractive. The key thing is you've got to have that quaternary HPGR in open circuit to avoid the classification issues. And once you get into this wet classification environment, you can take advantage of the wet grinding in something like a stirred mill. Another technology that has been in the news recently has been microwave enhanced ore breakage. Now, microwave treatment of ores was developed in the Soviet Union during the 1960s, so it's been around for quite a while. It's not really that new. It still requires crushing and grinding steps, so it's not going to be a replacement for tumbling mills and crushers and so on. All it basically can act as a pre-treatment step that will reduce the amount of energy supposedly being consumed in the crushing and in the grinding. So microwaves, not going to be a replacement for tumbling mills, but they can help reduce the need for tumbling mills in applications. Personally, I don't really see this being a big deal because it's been around for so long. So many people have looked at it, and it's just never become a viable technology financially. So I kind of suspect it's going to remain firmly in the university laboratories, and it's unlikely to make its way out into the industry anytime soon. Okay, coarse particle flotation. When done properly, this can very much reduce the amount of energy required for grinding as well. The way that you should be using coarse particle flotation is to reduce the amount of grinding you do in the grinding circuit. So you want to make as coarse a tailing as you possibly can coming out of your rougher flotation, where the rougher flotation would be one of these coarse particle floats. The idea is, instead of making a 200 micron tailing, you make a 3, 4, 500 micron tailing, something that's a lot coarser. You will spend a lot less energy grinding waste material if you are properly deploying coarse particle flotation, and if your ore is actually amenable to coarse particle flotation, because not all of them will be. So coarse particle flotation is not a replacement for tumbling mills in the sense that it does any crushing or grinding, but it can put you in a situation where that fourth stage HPGR circuit we talked about earlier, you might be able to take material straight out of a quaternary HPGR that's in open circuit and pass it through a coarse particle flotation machine, and you might be able to make a viable concentrate out of that can then go on to further grinding. So that's really the only application here where I can see you can get away from tumbling mills if coarse particle flotation can be mated to basically fine HPGR crushing in probably a fourth stage. So with that, I will wrap up and say that tumbling mills will remain a viable technology for the indefinite future. There are going to be situations where some of these other technologies will substitute in. So stirred mills following SAG mills, I think that's probably viable. HPGRs followed by ball mills, that's obviously viable. It's already being done. But it's not just the grinding and the crushing equipment that we're talking about here. The classification is actually very important as well. And in fact, that's what kills some of these options. If you have a very efficient grinding application like these vertical roller mills, but they're mated with some very inefficient classifiers, that whole concept can just fall apart because the classification can be very inefficient. The classification circuit that goes with certain grinding and crushing equipment can kill that option as a viable option. So what are the applications of alternative technologies that are most likely to displace tumbling mills? Well, we've already talked about tertiary HPGRs for competent coarse material. I think that's been demonstrated. Not all ores are going to be amenable to this. If you have an ore that has a very low crushing work index, it's a low competency, and a very high ball milling work index, that's an ore you should probably be using in a SAG mill or an AG mill. HPGRs are probably not a good choice for that particular ore, and there are certain climate conditions where HPGRs are not going to be desirable. Stirred mills following SAG mills, I think that's viable, but particularly for low tonnage operations and medium-sized tonnage operations. The issue with stirred mills, as we described, you can't build them big enough to take over from the great big ball mills and some of the great big tumbling mills that we have. Can you put a tertiary HPGR and a stirred mill together? The answer is probably not, at least not yet. That the product size range of the HPGR and the feed size range where you can do stirred milling, those two don't fit together unless you go to a fourth stage of HPGR, perhaps open circuit. We'll have to try that and see if it works. That might be the one application where you could eliminate tumbling mills altogether from a circuit using some of the technologies that we've described. So with that, I'll say thank you very much for your kind attention. I will again say thank you very much to the organizers at InterMet for allowing me to give this virtual keynote speech. I look forward to seeing all of you again in person at a future conference. And with that, I'll say thank you. Enjoy the rest of the conference, and bye-bye.